Tonight, we're going to travel to the edge of everything. Not to the edge of our galaxy, not to the edge of the observable universe. We are going to something even more fundamental. We are going to the wall of light that surrounds us in every direction, a barrier so ancient that it predates every star, every galaxy, every structure we can see. This wall has a name. Scientists call it the cosmic microwave background. And here is what most people do not realize. When you look at this ancient light, you're not just seeing the oldest thing in the universe. You're seeing the moment the universe itself became visible. Before this wall, there was nothing to see. The universe was darkness made of fire. And what exists beyond it might change everything you think you know. Before we go any further, if you find these kinds of deep explorations fascinating, a quick like or subscribe really helps the channel grow. It is a small gesture, but it makes a huge difference for me. I really appreciate it. Now, let's begin. Let us start with something that might seem strange. Right now, at this very moment, you are surrounded by ancient light. It is everywhere. It fills every cubic centimeter of space around you. It is passing through your body as you read these words, and it has been traveling toward you for almost 14 billion years. This light is so old that when it first began its journey, there were no stars, there were no galaxies, there were no planets. The universe was completely different from what we see today. It was a hot, dense fog of particles, nothing like the cold, dark, star-filled cosmos we are familiar with. This was a universe in its infancy, a universe that had not yet learned how to make the structures we take for granted. This ancient light has a name. Scientists call it the cosmic microwave background, or CMB for short. It's one of the most important discoveries in the history of science, and yet most people have never heard of it. They do not know it exists. They do not know that it surrounds them from every direction, filling all of space with its faint, ancient glow. They walk through life bathed in radiation from the beginning of time, completely unaware. The cosmic microwave background is, quite literally, the oldest light in the universe. It is light that has been traveling across space for approximately 13.8 billion years. Nothing we can see is older than this. When you look at distant galaxies through a telescope, you are seeing light that might be a few billion years old. Impressive, certainly. But when you look at the cosmic microwave background, you are seeing light that is almost as old as the universe itself. You are looking at the beginning. But here is what is truly remarkable. This ancient light is not coming from any particular direction. It is not like looking at a star or a galaxy, where you point your telescope at a specific spot in the sky. The cosmic microwave background comes from everywhere. It fills the entire sky uniformly. No matter which direction you point your instruments, you will detect it. It is above you and below you. It is to your left and to your right. It is in front of you and behind you. It surrounds you completely, like being inside a cosmic eggshell of ancient radiation. This creates a strange picture if you think about it carefully. Picture the geometry of this. No matter which direction astronomers point their instruments, they detect the same signal at the same distance. We exist at the center of a sphere whose surface is made of time itself, a temporal horizon painted in microwave light. It is like being inside a cosmic snow globe, with the ancient light forming the globe's shell. You cannot escape it. You cannot go around it. No matter where you are in the universe, you would see this same sphere of ancient light surrounding you. To understand what the cosmic microwave background really is, we need to understand when it was created. And To understand that, we need to go back to the beginning. Not just the beginning of Earth or our solar system or even our galaxy. We need to go back to the beginning of everything. We need to go back to the moment of creation itself. About 13.8 billion years ago, the universe began in an event we call the Big Bang. Now, the Big Bang was not an explosion in space like a bomb going off. This is a common misconception that trips up many people. It was an expansion of space itself. Space did not exist before the Big Bang, at least not in any way we can comprehend. There was no empty void waiting to be filled with matter and energy. There was no dark vacuum sitting there for the Big Bang to happen inside of. Space and time themselves came into existence with the Big Bang. The universe did not expand into anything. Space itself stretched and grew, carrying everything along with it. In the first moments after the Big Bang, the universe was unimaginably hot and dense. We are talking about temperatures of trillions of degrees, conditions so extreme that normal matter could not exist. The universe was filled with a seething soup of fundamental particles and energy. Quarks and antiquarks collided and annihilated. Photons bounced back and forth at incredible speeds. The laws of physics themselves were different at these extreme energies, unified in ways we are still trying to understand. As the universe expanded, it cooled. Think of it like a gas expanding. When you compress a gas, it heats up. When you let it expand, it cools down. You experience this every time you use a compressed air can. The air comes out cold because it is expanding rapidly. The universe was doing something similar, but on a cosmic scale. As space itself stretched and expanded, the energy in it became more spread out and the temperature dropped. For the first few 100,000 years, even though the universe was cooling, it was still incredibly hot. Hot enough that atoms could not form. This might seem strange because we think of atoms as the basic building blocks of matter. But atoms require electrons to be bound to atomic nuclei. At the temperatures that existed in the early universe, electrons were being ripped away from protons as fast as they could combine. The universe was filled with what physicists call a plasma, a soup of charged particles, free electrons and protons careening around at tremendous speeds. A plasma is sometimes called the fourth state of matter, alongside solid, liquid, and gas. It behaves differently from ordinary matter because the particles in it are electrically charged. On Earth, you encounter plasma in lightning, in the sun, and in those decorative plasma balls you might have seen in science stores. But the plasma that filled the early universe was far more extensive and far hotter than anything we create on Earth. It filled all of space, from one end of the universe to the other. And here is the key point. Light cannot travel freely through plasma. When light encounters a free electron, the electron scatters the light, sending it off in a random direction. This happens over and over again. A photon of light might travel a short distance, hit an electron, scatter off in some random direction, travel a bit more, hit another electron, scatter again. The light is constantly bouncing around, unable to go anywhere in a straight line. It is trapped, imprisoned by the electrons, unable to carry information from one place to another. Imagine trying to see through thick fog. The fog is made of tiny water droplets that scatter light. A photon of light enters the fog, bounces off a droplet, goes a different direction, bounces off another droplet, and so on. The light cannot travel through in a straight line. That is why fog looks white and opaque. The light is being scattered in all directions. No information can pass through. You cannot see what is on the other side. The early universe was like that, but much more extreme. It was not just fog, it was a completely opaque wall of plasma. Light could not travel through it. If you had been there somehow, you would not have been able to see anything. There would have been no vision, no sight, no images forming. Just brightness everywhere, light bouncing around constantly, never getting anywhere. An infinite prison of bouncing photons. This period of the universe's history is sometimes called the Dark Age, which is a bit of a misnomer because it was not dark at all. It was blindingly bright, but it was dark in the sense that no information could travel on light. Nothing could be seen because light could not go from one place to another. It was dark in the sense that no images existed, no patterns, no structure that could be perceived, just endless, uniform brightness without form. But the universe kept expanding. And as it expanded, it kept cooling. The temperature dropped relentlessly, degree by degree, as space stretched and the energy spread out. And finally, about 380,000 years after the Big Bang, the temperature dropped to a critical point. It reached about 3,000 degrees Kelvin, roughly half the temperature of the surface of the Sun. Still incredibly hot by everyday standards. But something remarkable was about to happen. At this temperature, something revolutionary occurred. The universe became cool enough for atoms to form and stay together. Electrons could finally join with protons to create neutral hydrogen atoms without immediately being knocked loose again. This process is called recombination, even though it is actually the first time electrons and protons combined. Not a recombination of something that had been combined before. The name is historical and has stuck, even though it is technically inaccurate. Scientists have a habit of keeping confusing names long after anyone remembers why they were chosen. When this happened, something incredible occurred. The fog lifted. The universe, which had been opaque for 380,000 years, suddenly became transparent. Light could finally travel in straight lines. The photons that had been bouncing around randomly for hundreds of thousands of years were suddenly free. They could finally go somewhere. The prison walls had vanished. And they did. Those photons, released at the moment of recombination, have been traveling ever since. They have been traveling for about 13.8 billion years. They have crossed almost the entire observable universe, and now, today, some of them are reaching us. They are entering our telescopes and our detectors. They are bringing us news from the beginning of time. That is what the cosmic microwave background is. It is the light that was released at the moment of recombination. It is the first light that could travel freely through the universe. Everything before that moment is hidden from us. We cannot see it directly because light could not travel back then. The cosmic microwave background is like a curtain drawn across the early universe, revealing everything after but hiding everything before. It is a wall, a barrier, a horizon beyond which we cannot see using light. The discovery of the cosmic microwave background is one of the great stories in the history of science. It happened almost by accident, and the scientists who discovered it initially had no idea what they had found. They were looking for something completely different, and they stumbled upon one of the most important discoveries in human history. In 1964, two scientists at Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson, were trying to use a large horn-shaped antenna to study radio signals from our galaxy. The antenna had been built for early satellite communication experiments, but it was now being repurposed for radio astronomy. Penzias and Wilson wanted to make precise measurements of radio emissions from the Milky Way. They needed the antenna to be as sensitive as possible, which meant eliminating all sources of noise. There was a problem. No matter what Penzias and Wilson did, they could not get rid of a persistent noise in their data. There was a faint hiss, a constant background signal that appeared in every direction they pointed the antenna. It was like a whisper that refused to go away, no matter how they tried to silence it. They tried everything to eliminate it. They thought it might be interference from nearby New York City. Radio waves from the city could theoretically be contaminating their measurements. They pointed the antenna away from the city. The noise was still there. They thought it might be a problem with the equipment. They checked every connection, every component. They tested every circuit. The noise persisted, steady and unchanging. Then they noticed something. Pigeons had been nesting in the antenna. The horn-shaped antenna made an attractive home for birds, and pigeons had moved in. The scientists thought maybe the pigeon droppings were causing the noise somehow. Perhaps the droppings were radiating heat or causing electrical problems. They cleaned out the antenna thoroughly, removing the pigeons and all their droppings. They scrubbed every surface. The noise was still there. The noise was coming from everywhere in the sky, equally from all directions. It was extremely faint, corresponding to a temperature of only about 3 degrees above absolute zero. And it would not go away no matter what they did. It was the most frustrating noise they had ever encountered. What Penzias and Wilson did not know was that just a few dozen miles away, at Princeton University, a team of physicists led by Robert Dicker was building an antenna specifically to look for this exact signal. Dicker and his colleagues had predicted that if the Big Bang Theory was correct, there should be a faint glow of microwave radiation filling the entire universe. It would be the leftover heat from the Big Bang itself, cooled down over billions of years to just a few degrees above absolute zero. They called it the cosmic fireball radiation. The Princeton team was building their own antenna to detect this predicted radiation. They were racing to be the first to find it. But they did not know that Penzias and Wilson had already found it, completely by accident, and were trying desperately to get rid of it. When Penzias and Wilson learned about Dicker's work, everything clicked into place. The noise they could not eliminate was not noise at all. It was the most ancient light in the universe. It was the cosmic microwave background. They had accidentally discovered one of the most important pieces of evidence for the Big Bang Theory. According to legend, when Dicker received the phone call from Penzias and Wilson describing their mysterious noise, he hung up the phone, turned to his colleagues and said, "Boys, we've been scooped." They had been beaten to the discovery they had been working so hard to make. Penzias and Wilson won the Nobel Prize in Physics in 1978 for their discovery. The cosmic microwave background became one of the strongest pieces of evidence that the Big Bang actually happened. It was a prediction of the theory that had been confirmed by observation. Science works by making predictions and then testing them. The CMB was a prediction that turned out to be correct, and that made the Big Bang Theory much more credible. But there was something puzzling about the early measurements. The cosmic microwave background appeared to be almost perfectly uniform. No matter which direction you looked, you measured the same temperature, about 2.7 degrees Kelvin. The differences, if any, were too small to detect with the instruments of the time. The CMB seemed to be perfectly smooth, a featureless glow with no structure at all. This was actually a problem. If the universe had been perfectly uniform after the Big Bang, with exactly the same density everywhere, then gravity would have had nothing to work with. There would have been no slightly denser regions to collapse and form galaxies. Gravity pulls matter toward denser regions. If everything is perfectly uniform, there are no denser regions. Gravity has nothing to do. The universe should remain completely smooth, with no structure at all. Obviously, the universe is not smooth. We have galaxies. We have clusters of galaxies. We have enormous structures spanning hundreds of millions of light years. The universe is full of structure at every scale. Something must have provided the seeds for all this structure. There must have been tiny variations in the early universe, slightly denser regions that eventually collapsed to form everything we see. In 1992, NASA's Cosmic Background Explorer satellite, known as COBA, made a breakthrough discovery. It detected extremely tiny variations in the cosmic microwave background. The variations were incredibly small, only about 1 part in 100,000. If the average temperature was 3 degrees, the variations were about 30 millionths of a degree. Almost undetectable, almost nothing. But they were there. The early universe was not perfectly uniform. It had tiny ripples, almost imperceptible fluctuations in density, and those tiny fluctuations were the seeds of everything. They were the embryonic galaxies, the primordial structures that would eventually grow into the cosmic web of galaxies and clusters we see today. Without those tiny ripples, we would not exist. The discovery of these fluctuations earned George Smoot and John Mather the Nobel Prize in Physics in 2006. Smoot famously described seeing these fluctuations as like seeing the face of God. It was a look back to the very beginning, to the seeds from which everything grew. It was a photograph of the embryonic universe, showing the tiny imperfections that would eventually become everything we know. Since COBE, we've launched even more sensitive satellites to study the cosmic microwave background. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, mapped the CMB with much greater precision. It could see features that COBE had missed, subtle patterns in the ancient light. The Planck satellite, launched by the European Space Agency in 2009, produced even more detailed maps. Each generation of instruments has revealed more detail, more information, more secrets hidden in the ancient light. These maps are extraordinary. They show the entire sky in microwave light, color-coded to show the tiny temperature variations. The maps look almost like abstract art, swirls of blue and red and yellow, showing regions slightly cooler or slightly warmer than average. But they are not art. They are a photograph of the universe when it was only 380,000 years old. Think about what that means. When you look at these maps, you are seeing the universe as it was 13.8 billion years ago, minus 380,000 years. You are seeing the universe before any stars existed, before any galaxies had formed. You are seeing the raw material from which everything was built. You are looking at your own ancestry, at the cosmic seeds from which you eventually grew. The cosmic microwave background is often called the surface of last scattering. This is because it is the last place where light was scattered before it could travel freely. Everything we see in the universe, all the stars and galaxies, is in front of this surface. The surface itself is like a wall, a barrier beyond which we cannot see using light. It marks the edge of the visible universe, but there is something even more profound to understand. This wall is not a physical thing sitting at some location in space. You cannot travel to the surface of last scattering and visit it like you might visit another planet. The surface of last. Scattering is actually a moment in time, frozen into light that has been traveling toward us ever since. Every direction you look, you are seeing light that was released at the same cosmic moment, 380,000 years after the Big Bang. But because light takes time to travel, and because the universe has been expanding, this light has been traveling for almost 14 billion years to reach us. The wall we see is not in space, it is in time. It is a temporal horizon, not a spatial one. This also means something strange about what we are actually seeing. The light from the cosmic microwave background started its journey from points that were much closer to us back then. The universe was much smaller. Everything was more compressed. But during the time this light has been traveling, the universe has expanded enormously. The points that emitted that light are now much, much farther away. In fact, due to the expansion of the universe, the regions that emitted the CMB, light we see today are now about 46 billion light years away from us. The light has been traveling for almost 14 billion years, but the expansion of space has carried its source much farther away. Space has been stretching the whole time, moving the source farther and farther away even as its light approached us. This creates the observable universe. The observable universe is roughly 93 billion light years in diameter, a sphere centered on us. Not because we are special, but because light has only had a finite time to reach us, and the universe has been expanding during that time. The edge of the observable universe is approximately the same as the surface of last scattering. Beyond it, we cannot see. Not because there is nothing there, but because light from beyond has not had time to reach us yet. The cosmic microwave background is our horizon. It is the wall that marks the edge of everything we can observe. And the most profound question is what exists beyond it? What came before? What is out there, past the wall of ancient light? But before we venture beyond, we should appreciate just how remarkable this discovery was. For most of human history, people had no idea this ancient light existed. They looked up at the stars and saw points of light, but they had no conception that the entire sky was glowing with radiation from the beginning of time. Even after the telescope was invented, even after we understood that stars were distant suns and that our galaxy was one of many, we still did not know about the CMB. The discovery changed everything. It transformed cosmology from philosophy into hard science. Before the CMB was found, the Big Bang Theory was just one of several competing ideas about how the universe began. Some scientists favored the steady state theory, which proposed that the universe had no beginning, that it had always existed in more or less its current form, with new matter continuously being created to replace what expanded away. The steady state theory was elegant and avoided the uncomfortable question of what happened before the beginning, but the CMB killed the steady state theory. The steady state model had no explanation for why the universe should be filled with this uniform microwave radiation. The Big Bang model predicted it. When the prediction was confirmed, the debate was settled. The universe had a beginning. The Big Bang happened. This is how science works. Theories make predictions. Observations test those predictions. Theories that fail are abandoned. Theories that succeed gain credibility. The CMB was not just a discovery. It was vindication for an entire way of thinking about the cosmos. The CMB also changed how we think about observation and knowledge. Before its discovery, most astronomical observations were about specific objects, stars, galaxies, nebulae. The CMB is different. It is everywhere. It is not an object we can point to. It is the universe itself, filling all of space, surrounding us completely. Looking at the CMB is not like looking at something out there. It is like being inside something. We are embedded in the ancient light, swimming in radiation from the dawn of time. This creates a strange relationship between the observer and the observed. When you study the CMB, you are not separate from what you are studying. You are part of it. The same universe that produced the CMB also produced you. The fluctuations that appear in the CMB eventually became the galaxies that contain the stars, that have the planets that support the life that asks the questions. You are the CMB, evolved. You are ancient light that learned to think. To answer that question, we need to understand more about what the CMB actually tells us. We need to look deeper into those tiny fluctuations and understand what they mean. Because hidden in those almost imperceptible variations is information about the very earliest moments of existence. Hidden in that ancient light are the answers to some of humanity's deepest questions. To truly understand the cosmic microwave background, we need to journey back in time, not just to 380,000 years after the Big Bang, but even further. We need to understand what the universe was like before the CMB was released. We need to understand the cosmic dark ages, when the universe was a blazing fog of plasma, and light itself was trapped. We need to go to times and conditions that defy ordinary imagination. Let us start at the very beginning, as close to time zero as physics allows us to go. In the first tiny fraction of a second after the Big Bang, the universe was in a state we can barely comprehend. It was unimaginably hot, unimaginably dense, and unimaginably small. All the energy that now fills the observable universe was compressed into a region smaller than an atom. At these extreme conditions, the laws of physics as we know them break down. We do not have a complete theory that can describe what happened at the very first instant. This is sometimes called the Planck epoch, a period lasting about 10 to the minus 43 seconds after the Big Bang. That is an inconceivably short time, a decimal point followed by 42 zeros and then a 1. During this time, all four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, may have been unified into a single force. The universe was so hot that normal concepts of space and time do not apply. We do not understand the Planck epoch. Our theories break down. General relativity, Einstein's theory of gravity, predicts infinities at these conditions. Quantum mechanics, our best theory of the very small, gives nonsensical answers. We need a theory of quantum gravity to understand this era, and we do not have one yet. String theory and loop quantum gravity are candidates, but neither is complete. The very beginning of the universe remains shrouded in mystery. As the universe expanded, it cooled rapidly. After about 10 to the minus 36 seconds, something extraordinary may have happened. Many physicists believe the universe underwent a period of incredibly rapid expansion called inflation. During inflation, the universe expanded by a factor of at least 10 to the 26th, possibly much more. That is a 1 followed by 26 zeros. Distances that were smaller than an atom suddenly became larger than the observable universe today. Inflation is a theory, not confirmed fact, but it explains many features of the universe that would otherwise be mysterious. We will talk more about inflation later when we discuss what might exist beyond the observable universe. For now, just know that most cosmologists believe something like inflation happened, even if we do not understand exactly how or why. The evidence for it is strong, even if the mechanism remains unclear. After inflation ended, the universe continued to expand and cool at a more modest rate. It was still incredibly hot, but now it was filled with a hot soup of fundamental particles. Quarks and electrons and photons and neutrinos and more exotic particles that do not exist in the universe today filled every corner of space. The universe was a seething cauldron of energy and matter. The particles in this primordial soup were constantly colliding, constantly interacting. Quarks combined and separated. Particles and antiparticles annihilated each other in bursts of energy. Photons bounced from particle to particle. It was chaos, but it was uniform chaos, the same everywhere in the universe. As the universe cooled further, quarks combined to form protons and neutrons. This happened when the universe was about 1 microsecond old. That is 1/1,000,000th of a second. The temperature had dropped to about 10 trillion degrees Kelvin. Still unimaginably hot by everyday standards, 100,000 times hotter than the center of the sun, but cool enough for protons and neutrons to exist without being immediately torn apart. By the time the universe was about 1 second old, it had cooled to about 10 billion degrees. Still incredibly hot, but cool enough for something important to happen. The universe became cool enough for neutrinos to stop interacting significantly with other matter. They decoupled from the rest of the universe and have been traveling freely ever since. There is actually a cosmic neutrino background, analogous to the cosmic microwave background, but made of neutrinos instead of photons. We have not been able to detect it directly yet because neutrinos are so hard to detect. Neutrinos are ghost-like particles that barely interact with anything. They can pass through light years of solid lead without hitting anything. Billions of neutrinos from the sun pass through your body every second, but you never notice them. The cosmic neutrino background is even harder to detect because the neutrinos are so low in energy, but we know it must exist. Between about 1 second and 3 minutes after the Big Bang, the universe was in a phase called nucleosynthesis. This is when the first atomic nuclei formed. Protons and neutrons combined to form the nuclei of hydrogen, helium, and trace amounts of lithium. The universe was like a giant nuclear reactor, fusing protons and neutrons into heavier elements. But nucleosynthesis was limited. The universe was expanding and cooling rapidly. By the time about 3 minutes had passed, the temperature had dropped too low for fusion to continue. The universe had made about 75% hydrogen by mass, about 25% helium, and tiny traces of lithium and other light elements, nothing heavier. The carbon in your body, the oxygen you breathe, the iron in your blood, none of that was made in the Big Bang. It was made later, in stars. This prediction of Big Bang nucleosynthesis has been confirmed by observations. When we look at the older stars and the gas between galaxies, we see exactly the mix of elements predicted. About 75% hydrogen, about 25% helium. This is one of the strongest pieces of evidence for the Big Bang theory. The theory predicted a specific ratio of elements, and we observe exactly that ratio in the oldest material we can find. But even after nucleosynthesis, the universe was still far too hot for atoms to form. Atoms are nuclei with electrons bound to them. The electrons orbit the nucleus, held in place by electromagnetic attraction. At temperatures above about 3,000 degrees, Electrons have too much energy to stay bound to nuclei. They are constantly being knocked loose by collisions with photons. And this is the key to understanding why the cosmic microwave background exists. The universe was filled with free electrons, particles carrying negative charge that were not bound to anything. And photons, particles of light, interact very strongly with free electrons. This interaction would keep light trapped for hundreds of thousands of years. When a photon encounters a free electron, it scatters. The photon's direction changes randomly. The photon might be heading north, hit an electron, and suddenly be heading east. It might travel a bit, hit another electron, and suddenly be heading down. If there are lots of free electrons around, photons cannot travel in straight lines. They bounce from electron to electron like a ball in a pinball machine. This process is called Thomson scattering, named after physicist J. Thomson. Thomson discovered the electron in 1897, showing that atoms were not the smallest units of matter. The scattering process that bears his name explains why the early universe was opaque. Light could not get from one place to another. It was constantly being scattered, bouncing around randomly, unable to carry information across any significant distance. Think of it like trying to pass a message through a crowded mosh pit. You hand a note to someone, but before they can deliver it, they collide with another person and the note gets passed in a random direction. It bounces from person to person, never reaching its destination, the message lost in chaos. That was light in the early universe. Every photon was a message that could never be delivered. The early universe was like that, but much more extreme. It was not just smoke, it was a plasma so dense that photons could not travel more than a tiny distance before scattering. The mean free path of a photon, the average distance it could travel before hitting an electron, was incredibly short. Light was completely trapped. To understand how trapped these photons were, consider this analogy. Imagine you're trying to walk through a crowded room. At first, there are only a few people, and you can walk in a straight line to the exit. But as more people enter the room, you start bumping into them. You get deflected. Your path becomes random. If the room gets crowded enough, you cannot make any progress at all. You are stuck, bouncing from person to person, never getting anywhere. The early universe was like that for photons, but much worse. The crowd was so dense that photons could barely move at all. They were ping-ponging off electrons constantly, their paths utterly randomized, their journeys going nowhere. A photon might have been generated at some point in the universe, but it would never get to show us what that point looked like. It would be scattered so many times that all directional information would be lost. This is why the early universe was hidden from us. Not because it was dark, but because the light could not escape. The universe was brilliant with energy, but that brilliance was contained, trapped, unable to flow. It was like a furnace with no windows, heat and light churning inside, but nothing getting out. This state persisted for about 380,000 years. For all that time, the universe was filled with light, but the light could not go anywhere. It was trapped, bouncing around, contained within the plasma like water in a sealed container. The universe was bright everywhere, but nothing could be seen. Information could not flow. The cosmos was blind. During this period, the universe was nearly featureless. The plasma was almost perfectly uniform. There were tiny fluctuations in density, regions very slightly denser or less dense than average, but they were almost imperceptible. These fluctuations were the seeds of future structure, but at this point, They were barely detectable, just 1 part in 100,000. The universe was smooth to an astonishing degree. The temperature gradually dropped as the universe expanded. The expansion of space stretched everything out, spreading the energy thinner, lowering the temperature bit by bit. At 380,000 years, it had fallen to about 3,000 degrees Kelvin. This is still incredibly hot by standards, about half the temperature of the sun's surface. You couldn't survive there, but it was cool enough for something revolutionary to happen. At 3,000 degrees Kelvin, recombination finally occurred. As I described earlier, this was the moment when electrons could bind to protons, forming neutral hydrogen. But let me now take you deeper into what this transition actually felt like on a cosmic scale. Imagine being there at that moment. For hundreds of thousands of years, you could not see anything. The universe was a blazing fog. Then, over a period of thousands of years, the fog begins to clear. Slowly, very slowly, visibility increases. Where before you could see nothing, now you can see a short distance, then farther still. The universe is opening up, revealing itself, becoming transparent for the first time. And as the fog clears, the photons that have been trapped are set free. They race outward at the speed of light, finally able to travel in straight lines after eons of random bouncing. They carry with them a snapshot of the universe at that moment, the temperature, the density, the tiny fluctuations that would become everything. They are like messengers released from a prison, carrying information that had been locked away since the beginning of time. Those messengers have been traveling ever since. Some of them are reaching Earth right now. Every second, photons from the cosmic microwave background are entering our telescopes, our radio dishes, our detectors. They have been traveling for almost 14 billion years to deliver their message, and we have learned to listen. At the moment of release, these photons had a temperature of about 3,000 degrees Kelvin. They were visible light, mostly in the orange-red part of the spectrum. If you could somehow transport yourself back to that moment, you would see the sky glowing with an almost uniform reddish-orange light in every direction. It would be like being inside a furnace that filled all of space, bright, hot, and featureless. But since then, those photons have been traveling through an expanding universe. As space expands, the wavelength of light traveling through it stretches. This is called cosmological redshift. It is different from the Doppler shift you might know about, where light changes color because its source is moving. This is space itself stretching, carrying the light wavelengths with it. The light is stretched by the expansion of space itself. Over almost 14 billion years, the universe has expanded by a factor of about 1,100. The wavelength of the CMB photons has stretched by the same factor. Light that started at 3,000 degrees Kelvin in the visible orange-red spectrum has been stretched into the microwave range. The temperature now, as measured by the energy of the photons, is only about 2.7 degrees Kelvin, almost absolute zero. The hot glow has become a cold whisper. This is why it is called the cosmic microwave background. The light is now in the microwave part of the electromagnetic spectrum, similar to the microwaves in your kitchen microwave oven, though much fainter. It is no longer visible to human eyes. You need microwave detectors to see it, but it is there, filling all of space, just waiting for instruments sensitive enough to detect it. The uniformity of the CMB is both remarkable and meaningful. When we measure the temperature of the CMB in different directions, we find it is almost exactly the same everywhere. 2.725 degrees Kelvin in every direction, with variations of only about 1 part in 100,000. The universe was incredibly uniform at this time. The fluctuations that would become galaxies and stars were almost imperceptible. This uniformity tells us something profound about the early universe. It tells us that the universe was in thermal equilibrium. Every part of the observable universe had the same temperature because every part had been in contact with every other part. Energy had been exchanged and distributed evenly. Heat had flowed from hot regions to cold regions until everything was the same temperature. But wait, this creates a puzzle. If you look at the CMB in opposite directions of the sky, you are seeing light from regions that are now about 93 billion light years apart. At the time the CMB was released, those regions were about 90 million light years apart. But the universe was only 380,000 years old at that time. Light could only have traveled 380,000 light years. How could regions 90 million light years apart have exchanged energy and reached the same temperature? Light could not have traveled between them. They could not have been in causal contact. Nothing, not even information, can travel faster than light. And yet, they have exactly the same temperature. This seems impossible. This is called the horizon problem, and it is one of the main reasons physicists believe in inflation. If the universe underwent a period of extremely rapid expansion early on, then regions that are now far apart could have been in contact before inflation stretched them away from each other. They reach thermal equilibrium first, sharing energy and reaching the same temperature. Then inflation stretched them apart, separating them by enormous distances, but preserving their shared temperature. The moment of recombination was not instantaneous. It took time for all the free electrons to combine with protons. The transition from an opaque plasma to a transparent gas happened over a period of about 120,000 years. During this time, the probability of a photon being scattered decreased gradually as more and more electrons combined into atoms. This means the surface of last scattering has some thickness. It is not like a glass window that light passes through instantly. It is more like fog that gradually clears as you walk through it. The CMB photons were released over a range of times, corresponding to a range of distances. The surface has depth. This affects what we see in the CMB. Very small features in the CMB are smeared out because photons from different depths of the surface of last scattering are mixed together. It is like looking at a photograph that is slightly out of focus. The largest features are still sharp, but the smallest details are blurred. This sets a limit on how much fine detail we can see in the CMB. The thickness of the last scattering surface also means we are not seeing a single moment in time, but rather a range of moments. We are seeing the universe in the process of becoming transparent, not a single frozen instant. The CMB is a time-lapse photograph, not a snapshot. After recombination, the universe entered what is called the Dark Ages. This is a somewhat confusing name because it was not dark in the sense of no light existing. The CMB, photons were streaming through space, but it was dark in the sense that there were no other sources of light. No stars had formed yet. No galaxies existed. The universe was filled with neutral hydrogen gas, slowly cooling in the darkness. The small fluctuations that had existed in the plasma began to grow. Regions that were slightly denser than average had slightly stronger gravity. They pulled in more matter from their surroundings, becoming denser still. This is the process of gravitational collapse, and it would eventually lead to the formation of the first stars and galaxies. But gravitational collapse is slow. It takes time for matter to fall inward, for gas to compress and heat up, for the conditions needed for nuclear fusion to develop. The Dark Ages lasted for about 100 million years, perhaps 200 million years. For all that time, the universe was filled with hydrogen gas and the fading glow of the CMB, but nothing else. No stars, no light sources, just gas and darkness. Then the first stars ignited. These were massive stars, probably hundreds of times more massive than our sun. They formed from the primordial hydrogen and helium, compressed by gravity until their cores were hot enough for nuclear fusion. When they turned on, they flooded the universe with ultraviolet light, beginning the process of reionization, where neutral hydrogen atoms were split apart again. This began a new phase of cosmic history, but it did not affect the CMB. The cosmic microwave background had already been released. It was already traveling through space. The formation of stars and galaxies happened in front of the CMB, between us and the surface of last scattering. When we look at the cosmic microwave background today, we are looking through all the subsequent history of the universe. We are looking past all the stars and galaxies that have formed, past the billions of years of cosmic evolution, back to that moment 380,000 years after the Big Bang when light first broke free. The CMB is like a photograph of the baby universe. Everything that has happened since is in front of the photograph. We cannot see through the photograph to what came before. The surface of last scattering is a barrier, a wall that separates what we can see from what we cannot. But the remarkable thing is how much information is encoded in that photograph. The tiny fluctuations in the CMB are not random noise. They have patterns, correlations, specific features that tell us about the physics of the early universe. By studying these patterns, we have learned more about the universe than anyone could have imagined when Penzias and Wilson first detected that mysterious hiss in their antenna. The cosmic microwave background is not just old light. It is a treasure trove of information about the universe. Hidden in those tiny temperature fluctuations are patterns that reveal the age of the universe, its shape, its composition, and its ultimate fate. Scientists have called the CMB the fingerprint of creation, and they are not exaggerating. These faint ripples in the microwave sky contain the answers to some of humanity's deepest questions. When you look at a detailed map of the CMB, you are looking at something almost miraculous. You are seeing the universe as it was before any stars existed. You are seeing the raw material from which everything was built. Every galaxy you have ever seen, including our own Milky Way, began as a tiny hotspot in this ancient light. Every star, every planet, every moon, every asteroid, every grain of dust, all of it traces back to these primordial fluctuations. And so do you. Every proton in your body dates back to the first second of existence. The hydrogen atoms that make up most of your mass were forged in those first minutes. You are not merely observing the early universe, you are made of it. The hydrogen atoms that make up most of your mass were created minutes after the Big Bang. The heavier elements were forged later, in stars, but the protons in their nuclei date back to the first second of existence. When you look at the CMB, you are looking at your own origin, at the seeds from which you grew. Let us start with the fluctuations themselves. When you look at a map of the CMB, you see a pattern of slightly warmer and slightly cooler regions. The differences are tiny, about 1 part in 100,000. If the average temperature is about 2.7 degrees Kelvin, the hotspots are about 30 millionths of a degree warmer, and the cold spots are about 30 millionths of a degree cooler. Almost nothing. Almost invisible. These fluctuations might seem like noise, like random static on a television screen, but they are not random at all. They have very specific statistical properties that tell us about the physics of the early universe. The pattern of hot and cold spots is not chaotic. It has structure. It has meaning. The fluctuations originated as quantum fluctuations in the very early universe, probably during inflation. Quantum mechanics tells us that empty space is not really empty. It is filled with virtual particles constantly popping in and out of existence, with energy fluctuations that appear and disappear. Even a perfect vacuum seethes with activity at the quantum level. During inflation, these tiny quantum fluctuations were stretched to enormous scales and frozen into the fabric of space. Fluctuations that were smaller than an atom became fluctuations spanning millions of light years. The quantum became cosmic. The uncertainty principle wrote itself across the sky. After inflation, these fluctuations became density fluctuations. Slightly denser regions of the universe containing slightly more matter than average. In the plasma that filled the early universe, these density fluctuations set up sound waves. Yes, sound waves. The early universe was ringing like a bell. The plasma was a fluid, and like any fluid, it could support sound waves. Density fluctuations created pressure differences, and pressure differences drove fluid motion, creating waves that propagated through the primordial plasma. But these were not ordinary sound waves. They were waves in a plasma that filled the entire universe. They were waves on a cosmic scale, with wavelengths of thousands of light years, and they lasted for hundreds of thousands of years, from the time the fluctuations were created until recombination. Think about what this means. The entire universe was vibrating. Every region of space was participating in a cosmic symphony, with sound waves of every size propagating in every direction. There was no silence anywhere. The universe was full of cosmic music, oscillations of density and pressure playing out across millions of light years. The speed of these sound waves was remarkable. In air on Earth, sound travels at about 340 meters per second. In the primordial plasma, sound traveled at about half the speed of light. This is because the plasma was so hot that the particles were moving at enormous speeds. The sound was carried by those fast-moving particles, and so the sound itself was extraordinarily fast. This fast speed meant that sound waves could travel enormous distances during the 380,000 years before recombination. A sound wave could cross about 500,000 light years in that time. This set the characteristic size of the largest oscillations we see in the CMB. When recombination happened, the waves froze. The plasma became neutral gas, and sound waves cannot propagate through neutral gas in the same way. The pattern of waves was frozen into the distribution of matter, like ripples frozen in ice. The music stopped, but the pattern of the music was preserved. The CMB shows us this frozen pattern. The slightly hotter and cooler regions correspond to the peaks and troughs of the sound waves at the moment of recombination. They are like a photograph of sound, an image of cosmic vibrations captured in light. We are seeing the universe singing. These sound waves have a particular property that is extremely useful. They have characteristic sizes. The largest waves, the fundamental mode, had just enough time to complete one oscillation before recombination. Smaller waves, the overtones, completed 2 oscillations, or 3, or more. These characteristic sizes show up as peaks in the CMB data. Scientists analyze the CMB using something called the power spectrum. This is a graph that shows how much variation there is at different scales. Large scales correspond to big hot and cold spots on the sky. Small scales correspond to tiny features. The power spectrum of the CMB has a series of peaks, corresponding to the different modes of sound waves in the early universe. The position of these peaks tells us something remarkable. The largest peak occurs at an angular scale of about 1 degree on the sky. This corresponds to the size of the fundamental sound wave at the moment of recombination. But the apparent size of this wave depends on the geometry of the universe. If the universe is flat, meaning space is not curved, then light travels in straight lines. The sound wave would appear a certain size. If the universe is positively curved, like the surface of a sphere, light would bend and the wave would appear larger. If the universe is negatively curved, like a saddle, light would bend the other way, and the wave would appear smaller. The CMB tells us that the first peak is at almost exactly the position predicted for a flat universe. This is one of the most important results from CMB observations. The universe appears to be flat, or very close to flat. Space is not curved on large scales. The geometry of the cosmos is Euclidean, the same geometry you learned in school. This flatness has profound implications. In general relativity, the curvature of the universe is determined by its total energy density. A universe with exactly the critical energy density is flat. More energy makes it positively curved. Less energy makes it negatively curved. The CMB measurements tell us that the universe has almost exactly the critical energy density. The total energy in the universe, including matter and radiation and whatever else might be out there, adds up to almost exactly the critical value. This is sometimes called the flatness problem because it seems like an incredible coincidence. Why should the universe be so precisely balanced? Inflation provides an explanation. One of the predictions of inflation is that it drives the universe toward flatness. No matter what curvature the universe started with, inflation stretches it so much that any curvature becomes undetectable. It is like inflating a balloon. The surface of a small balloon is noticeably curved, but if you inflate it to enormous size, any small patch of the surface looks flat. So the flatness of the universe, revealed by the CMB, is strong evidence for inflation. It is a prediction that has been confirmed by observation. The heights of the peaks in the CMB power spectrum tell us something else. They tell us about the composition of the early universe. The ratio of normal matter to dark matter affects how the sound waves behave. Dark matter does not interact with light, so it does not participate in the sound waves directly. But it does provide gravity, which affects how the waves evolve. From the CMB, we can determine that normal matter, the kind of matter made of protons and neutrons, the stuff that makes up everything we can see, makes up only about 5% of the total energy in the universe. Dark matter makes up about 27%, and the remaining 68% is something called dark energy. This is a stunning result. Everything we can see, all the stars and galaxies and planets and dust and gas, makes up only about 5% of the universe. The rest is invisible. Dark matter interacts gravitationally but does not emit or absorb light. Dark energy is even more mysterious. a form of energy that fills empty space and causes the expansion of the universe to accelerate. Let that sink in for a moment. You look up at the night sky and see thousands of stars. You use a telescope and see billions of galaxies. You think you are seeing the universe, but you are seeing only 5% of it. The other 95% is invisible. It is there, it affects everything, but we cannot see it directly. We can only infer its existence from the way it influences what we can see. It is as if you were studying an iceberg, but you could only see the tip above the water. You might think the tip is the whole thing, but beneath the surface there is vastly more, invisible but real, shaping the behavior of the tip in ways you might not understand unless you knew the hidden mass was there. Dark matter is the hidden mass of the universe. It outweighs normal matter by more than 5 to 1. It clumps together, forming enormous halos around galaxies. When galaxies form, they form inside these dark matter halos. The visible galaxy is like the tip of the iceberg. The dark matter halo is the invisible bulk beneath the surface. Dark energy is stranger still. It does not clump. It fills all of space uniformly, and it has a bizarre property. It causes the expansion of the universe to accelerate. Normal matter and dark matter both slow down expansion through their gravitational pull. Dark energy does the opposite. It pushes. It makes the universe expand faster and faster. We have no idea what dark energy is. It might be a property of empty space itself, what physicists call the cosmological constant. It might be some kind of field that fills the universe. It might be something else entirely. The CMB tells us it exists and how much of it there is, but not what it is. We know dark matter exists because we can see its gravitational effects. Galaxies rotate too fast for the visible matter alone to hold them together. Something invisible must be providing extra gravity. Galaxy clusters contain much more mass than we can see. Gravitational lensing, where gravity bends light, reveals invisible mass. And the CMB confirms it, showing that the early universe had more gravitational mass than normal matter alone could provide. Dark energy is even stranger. It was discovered in the late 1990s through observations of distant supernovae, which showed that the expansion of the universe is accelerating. The CMB provides additional confirmation. The total energy density of the universe equals the critical value, and the amounts of normal matter and dark matter do not add up to critical. Something else must be filling the gap. That something is dark energy. The nature of dark matter and dark energy remain two of the biggest mysteries in physics. We do not know what particles make up dark matter, despite decades of experiments trying to detect them. We do not know what dark energy is or why it has the value it does. The CMB tells us these things exist and how much of them there is, but it does not tell us what they are. The mystery remains. The CMB also tells us the age of the universe with remarkable precision. By combining all the information from the power spectrum, including the peak positions, peak heights, and overall shape, cosmologists can constrain the parameters of the universe very precisely. One of those parameters is the Hubble constant, which describes how fast the universe is expanding today. From the CMB data, the universe is about 13.8 billion years old. The uncertainty is only about 1%. This is one of the most precise measurements in all of cosmology. We know the age of the universe to within a few 100 million years. A remarkable achievement for creatures who have only been doing science for a few centuries. There is actually a bit of controversy here. Different methods of measuring the Hubble constant give slightly different results. The CMB gives one value. Observations of nearby supernovae and Cepheid variable stars give another value, slightly higher. The difference is small, but statistically significant. Cosmologists call this the Hubble tension, and there is ongoing debate about whether it indicates a problem with our measurements or new physics we do not yet understand. The tiny fluctuations in the CMB have a specific statistical pattern. They are what mathematicians call Gaussian random fluctuations. This means they follow a normal distribution, the familiar bell curve. Most fluctuations are close to the average, with fewer and fewer at larger deviations. This Gaussian nature is another prediction of inflation. The quantum fluctuations that inflation stretched into cosmic density fluctuations are inherently Gaussian. If the CMB fluctuations were non-Gaussian, it would be evidence against simple inflation models. So far, all measurements have confirmed that the fluctuations are Gaussian to high precision. But there is more. The fluctuations also have a specific pattern called the power spectrum. This describes how much variation there is at different scales. Inflation predicts that the power spectrum should be nearly scale invariant, meaning there is almost the same amount of variation at all scales. The CMB confirms this too, with a power spectrum that is very close to scale invariant, with just a small tilt. The CMB also shows us something called acoustic oscillations. These are the remnants of the sound waves I mentioned earlier. They show up not just as peaks in the CMB power spectrum, but also in the distribution of galaxies today. The sound waves in the early universe created a slight preference for matter to be separated by a particular distance. This distance is about 500 million light years in today's universe. When we map the distribution of galaxies, we see a slight excess of galaxy pairs separated by this distance. It is called the Baryon Acoustic Oscillation Scale, and it is a direct remnant of the sound waves that rang through the early universe. This is remarkable. The same waves that we see in the CMB, frozen at the moment of recombination, left their imprint on the distribution of matter. That imprint persists today, billions of years later, visible in the large-scale structure of galaxies. The universe remembers its sound waves. The CMB also has another property that provides additional information. It is polarized. Light is a wave, and that wave can oscillate in different directions. Normally, light from the sun or a light bulb oscillates randomly in all directions. But light can become polarized, with the oscillation aligned in a particular direction. The CMB is slightly polarized. This polarization was imprinted at the time of recombination, when photons scattered off electrons for the last time. The pattern of polarization contains additional information about the early universe. There are two types of polarization patterns in the CMB, called E modes and B modes. E modes arise from the same density fluctuations that cause the temperature fluctuations. They have been detected and studied in detail. B modes are more subtle. Some B modes come from gravitational lensing, where the gravity of intervening matter bends the CMB light and rotates its polarization. These have been detected too, but there is another potential source of B modes that has cosmologists very excited. Gravitational waves from inflation could produce B mode polarization in the CMB. If inflation happened, it would have produced ripples in space-time, gravitational waves, that would leave a distinctive pattern in the CMB polarization. Detecting these primordial gravitational waves would be a smoking gun for inflation. It would confirm that inflation happened and tell us about the energy scale at which it occurred. Several experiments are searching for this signal, including ground-based telescopes at the South Pole and in Chile, and proposed space missions. The search for primordial gravitational waves is one of the great quests of modern cosmology. If we find them, we will have direct evidence of what happened in the first tiny fraction of a second after the Big Bang. We will be seeing through the surface of last scattering, past the barrier that light cannot penetrate, into the era of inflation itself. This would be an extraordinary achievement. For all of history, we have been limited to seeing the universe as it was 380,000 years after the Big Bang. Gravitational waves would let us see back to less than a trillionth of a second after the Big Bang. It would be like being limited to seeing someone's childhood photographs and then suddenly getting a picture from the moment of their birth. The technology required to detect these gravitational waves is extraordinary. We are looking for polarization patterns in the CMB that are incredibly faint. The signal from primordial gravitational waves might be 1,000 times weaker than the already weak CMB polarization. It is like trying to hear a whisper in a hurricane, but scientists are patient and persistent. They build better instruments. They develop better analysis techniques. They keep trying. And eventually, they succeed. The history of science is full of impossible measurements that became possible through ingenuity and persistence. The detection of the gravitational waves from black hole mergers was thought to be impossible until LIGO did it. The detection of the CMB itself was accidental, found by scientists looking for something else. So far, no definitive detection has been made. There was a false alarm in 2014 when the BICEP-2 experiment announced detection of B modes from gravitational waves, but it turned out to be contamination from dust in our own galaxy. The search continues, and it is one of the most important ongoing efforts in cosmology. The CMB also tells us about the cosmic neutrino background. Remember, neutrinos decoupled from the rest of the universe about 1 second after the Big Bang, long before recombination. They have been traveling freely ever since, carrying information about that even earlier time. The cosmic neutrino background is a ghost from the past, invisible messengers from an era we cannot see with light. These neutrinos were created when the universe was less than 1 second old. They have been traveling ever since, filling all of space, passing through everything without interacting. Billions of them are passing through your body right now. Ancient travelers from the first second of existence. We cannot detect the cosmic neutrino background directly. Neutrinos interact so weakly with matter that detecting ones with such low energy is beyond our current technology. A neutrino can pass through a light year of solid lead without hitting anything. The cosmic neutrinos have even less energy than solar neutrinos, which are already difficult to detect. Catching these primordial ghosts would require technology far beyond what we have today. But the neutrinos affect the CMB indirectly. They contribute to the expansion rate of the universe and influence how structure forms. By analyzing the CMB, we can infer properties of the cosmic neutrino background. From the CMB, we know there are 3 types of neutrinos, matching what particle physics experiments tell us. We can also constrain the mass of neutrinos. The CMB data, combined with other observations, tells us that the sum of the masses of all neutrino types is less than about 0.12 electron volts. This is an incredibly precise measurement of a particle physics property from cosmological observations. It is remarkable that by studying the ancient light, we can learn about particles that do not interact with light at all. The CMB is a Swiss Army knife of cosmology, revealing information about every aspect of the early universe: dark matter, dark energy, neutrinos, the geometry of space, the age of the universe, the seeds of structure. All of this and more is encoded in the faint glow that fills the sky. The cosmic microwave background is, in many ways, the most important observable in cosmology. It tells us the age of the universe, its geometry, its composition. It confirms our theories of the Big Bang and inflation. It provides evidence for dark matter and dark energy. It shows us the seeds from which all structure grew, but it also represents a limit. The surface of last scattering is a wall beyond which we cannot see with light. The CMB is the oldest light we can ever detect. Everything before recombination is hidden from us, shrouded behind a veil of primordial plasma. Or is it? Is there any way to peer beyond the wall? Any way to see what the universe was like before light could travel? Any way to know what exists beyond the edge of what we can observe? So we have journeyed to the edge of the visible universe. We have seen the wall of ancient light that surrounds us. We have decoded the messages hidden in its faint glow. Now we face the ultimate question: what exists beyond? This question has haunted humanity since we first looked up at the stars. Every civilization has wondered what lies beyond the edge of the known. For most of history, the edge was the horizon, the line where land met sky. Then it was the ocean, vast and seemingly endless. Then it was our solar system. Then our galaxy. Now we have pushed to the ultimate edge, the edge of the observable universe itself, the boundary marked by the cosmic microwave background. And still we ask, what is beyond? This is not a simple question. It touches on the deepest issues in physics and cosmology. It forces us to confront the limits of what we can know and the nature of existence itself. The answer, to the extent we have one, might be the most profound thing we can say about the universe. Let us start with what beyond actually means. The cosmic microwave background represents a horizon, a limit to how far we can see using light. But it is not a physical barrier sitting somewhere in space. It is not a wall you could touch or bump into. It is a time barrier. We cannot see further back than 380,000 years after the Big Bang because the universe was opaque before then. Light from before that time never made it out. It was trapped, scattered, absorbed. We cannot see it because it does not exist anymore. But the universe existed before recombination. Those first 380,000 years happened. Matter was there. Energy was there. The universe was there. We just cannot see it directly with light. This is similar to how we cannot see inside the sun. The sun's interior is so hot and dense that light bounces around randomly, unable to escape. We see the surface of the sun, the photosphere, where light finally breaks free. But the sun has an interior. There are nuclear reactions happening at the core. We just cannot see them directly. The early universe is like that. The plasma that existed before recombination was like the interior of the sun, but filling all of space. We see the surface where light broke free, the surface of last scattering. But the interior, the era before recombination, existed and contained physics and processes that shaped the universe. What was happening in that hidden era? We cannot see it directly, but we can infer it. The fluctuations we see in the CMB carry information about earlier times. The physics equations that govern how fluctuations evolve allow us to run the clock backward, to figure out what conditions must have been like to produce what we observe. Going back in time, the universe becomes hotter and denser. The physics becomes more extreme. At some point, we reach the limits of our understanding. We know the equations of particle physics, tested in accelerators here on Earth, describe conditions up to energies of about 1 trillion electron volts. Beyond that, we are extrapolating, using theories that have not been tested. But most cosmologists believe we can extrapolate quite far. The physics of nucleosynthesis, when the first atomic nuclei formed, has been tested and confirmed. The physics of the electroweak phase transition, when the electromagnetic and weak nuclear forces separated, is reasonably well understood. Going further back becomes more speculative, but we have theories. And then we reach inflation. This is the key to understanding what might exist beyond the observable horizon. Inflation is the theory that the very early universe underwent a period of exponential expansion, growing by an enormous factor in a tiny fraction of a second. Inflation solves several puzzles about the universe. It explains why the universe is so flat. It explains why distant parts of the universe have the same temperature. The horizon problem I mentioned earlier, it explains where the initial fluctuations that seeded structure came from. It is not proven beyond doubt, but it is widely accepted among cosmologists. If inflation happened, it has a profound implication. The universe beyond what we can see might be much, much larger than the observable universe, perhaps infinitely larger. Here is why. During inflation, the universe expanded by at least a factor of 10 to the 26th. A region that was smaller than an atom became larger than the entire observable universe today. But inflation did not necessarily stop after that minimum amount of expansion. It might have continued much longer in some regions of space. In fact, many inflation models predict something called eternal inflation. Once inflation starts, it tends to keep going. It produces new regions of inflating space faster than inflation ends in existing regions. The result is that inflation never completely stops. There is always some part of the universe that is still inflating, producing more and more space. This is a mind-bending concept. Picture the universe as foam, like the bubbles in a bubble bath. New bubbles are constantly forming. Each bubble is a region where inflation has ended and normal expansion has taken over. These bubbles grow as inflation ends in regions around their edges. But between the bubbles, inflation continues, producing more space that then spawns more bubbles. Our observable universe would be the interior of one such bubble. We see a universe that looks roughly uniform because we are inside a single bubble, where inflation ended at about the same time everywhere. But beyond our bubble, beyond our horizon, there might be an infinite foam of other bubbles, each a universe unto itself. Some of these bubbles might have the same physics as ours. They might have galaxies and stars and planets. They might even have life. Other bubbles might have different physics. The laws of nature might not be the same everywhere. What we think of as fundamental constants might vary from bubble to bubble. This is an extraordinary possibility. The universe we see might be just one of an infinite number of universes, and we would never know. We could never travel to another bubble. We could never receive signals from another bubble. Each bubble universe is isolated, cut off from all the others by the inflating space between them. What this means is that our observable universe might be just one tiny bubble in an enormously larger cosmos. There might be other bubbles out there, other regions where inflation ended and normal expansion took over. These regions would be like ours, with their own matter and energy and potentially their own structures. But here is the catch. These other regions are beyond our horizon. They are so far away that light from them has not had time to reach us. And because the universe is expanding, they might be receding from us faster than light itself. They might be forever beyond our reach. This raises a philosophical question. If we can never observe these other regions, can we say they exist? Is this science or speculation? It is a fair question, and cosmologists debate it. Some argue that inflation is the best explanation for what we do observe, and eternal inflation is a natural consequence of many inflation models. If we accept inflation, we should accept its implications, even if we cannot directly test them. Others argue that talking about unobservable regions is stepping outside the bounds of science. There is no consensus on this. But it is worth noting that many scientific ideas involve entities we cannot directly observe. We believe in quarks, even though we have never seen an isolated quark. We believe in the interior of the sun, even though we have never directly observed it. The question is whether we have good theoretical reasons to believe something exists, and whether it is part of a framework that explains what we do observe. Beyond inflation, there are even more speculative ideas about what exists beyond our horizon. String theory, one of the leading candidates for a theory of quantum gravity, suggests that there might be additional dimensions of space beyond the three we are familiar with. These dimensions would be curled up very small, invisible to us, but they would affect the physics of the very early universe. String theory also suggests the possibility of a multiverse, a collection of universes with different properties. In some versions of the theory, different regions of space might have different values of fundamental constants. The strength of gravity, the mass of the electron, the value of the cosmological constant, all of these might vary from one region to another. If this is true, then our universe with its particular laws of physics might be just one of countless possibilities. Other universes might have completely different physical laws. Some might be able to support life, others might be barren, unable to form atoms or stars or planets. Think about what that means. In some of these other universes, the laws of physics might be such that atoms cannot form. No chemistry, no structure, just a featureless soup of particles that never combine into anything interesting. In others, stars might not be possible. No nuclear fusion, no light, no energy sources to power anything. In still others, the universe might collapse back on itself before anything interesting can happen, or expand so fast that matter never has time to clump together. Our universe has the right properties for complexity. Atoms can form, chemistry works, stars shine, planets coalesce, life evolves. These things are not guaranteed. They require the fundamental constants of physics to fall within very narrow ranges. Change the strength of gravity slightly, and stars either cannot form or collapse into black holes immediately. Change the strength of the electromagnetic force, and atoms fall apart. Change the mass of quarks, and protons and neutrons cannot exist. Why do the constants have the values they do? This is one of the deepest questions in physics. The constants appear to be tuned for complexity, for life, for us. But tuned by what? By whom? This raises the question of why our universe has the particular laws it does. Some physicists invoke the anthropic principle. Perhaps there are many universes with different laws, and we find ourselves in one that supports life because we could not exist in the others. It is not that our universe was designed for us. It is that we can only exist in a universe like ours. This is a strange kind of explanation. It is not like explaining why the sky is blue by pointing to the scattering of light. It is saying that the sky has to be blue for us to be here asking the question. It is a selection effect, not a cause. Some physicists find this deeply unsatisfying. They want a real explanation, a theory that predicts the values of the constants from deeper principles. Others find this unsatisfying. They hope for a deeper explanation, a theory that would predict the values of the fundamental constants from first principles. Maybe there is only one mathematically consistent set of laws, and we just have not figured out why yet. These are deep waters, and we are far from any definitive answers. But they show that the question of what exists beyond the observable universe touches on some of the most fundamental issues in physics. Let me bring this back to the cosmic microwave background. The CMB represents a horizon, but it is not the only horizon. There is also the cosmic event horizon, the maximum distance from which light can ever reach us given the accelerating expansion of the universe. You see, the universe is not just expanding. The expansion is accelerating, driven by dark energy. This means that distant galaxies are receding from us faster and faster. Some galaxies are already receding faster than the speed of light. Now, this does not violate relativity. The galaxies are not moving through space faster than light. Space itself is expanding, carrying them along. But the effect is the same. Light from these galaxies will never reach us. They are beyond our cosmic event horizon. The cosmic event horizon is even closer than the particle horizon, the edge of the observable universe. Galaxies we can see today, whose light has reached us, will eventually cross the event horizon and become invisible. In the very distant future, trillions of years from now, the only galaxies remaining in our sky will be those in our local group, gravitationally bound to us. Everything else will have faded beyond the event horizon, carried away by the expanding universe. This has a melancholy implication. Future astronomers, living trillions of years from now, might have no way of knowing the universe is expanding. They will see only their local group of galaxies, isolated in an otherwise empty cosmos. The cosmic microwave background will have redshifted so much that it will be undetectable. All the evidence for the Big Bang, all the clues we have used to figure out the history of the universe, will be gone. In a sense, we are living in a privileged time. We can see the universe's history written in the sky. Future civilizations might not be so lucky. But let us return to the question of what exists beyond. We have talked about inflation and the possibility of a much larger universe beyond our horizon. We have talked about the multiverse and the possibility of other universes with different laws. But there is another aspect to beyond that we should address. What existed before the Big Bang? This is perhaps the deepest question of all. The Big Bang was not just an event in space, it was the origin of space and time themselves, at least according to standard cosmology. There was no before because time itself began with the Big Bang. This is hard to wrap your head around. We are used to thinking of time as a river that flows forever, stretching back into an infinite past. But in Big Bang cosmology, time has a beginning. Asking what came before is like asking what is north of the North Pole. The question does not quite make sense. However, there are alternative views. Some theories suggest that the Big Bang was not the absolute beginning, but a transition from a previous state. There might have been something before, something that gave rise to our universe. One idea is called the cyclic universe. In this model, the Big Bang was not creation from nothing but a kind of cosmic bounce. The universe undergoes cycles of expansion and contraction. Our current expansion will eventually reverse, the universe will contract, and then bounce back in another Big Bang. This has happened before and will happen again, in an eternal cycle. In the cyclic model, time extends infinitely into the past and infinitely into the future. There was no first moment. There will be no last moment. The universe has always existed, cycling through phases of expansion and contraction, each cycle lasting perhaps 1 trillion years. Our Big Bang was just the beginning of our cycle, not the beginning of everything. This is an elegant idea because it avoids the troubling question of what came before the beginning. There was no beginning. There have always been cycles. The universe is eternal. But the cyclic model faces challenges. For one thing, each cycle would leave traces. Information from previous cycles might survive into the next. Physicists have looked for such traces and found nothing conclusive. The universe appears fresh, as if it really did begin with our Big Bang. Also, the discovery of dark energy complicates the cyclic model. Dark energy causes the expansion to accelerate. If dark energy persists, the universe will never contract. It will expand forever, faster and faster, eventually tearing apart even atoms. This does not fit the cyclic picture. Still, some versions of the cyclic model work around these problems. The ekpyrotic model, for instance, proposes that the cycles occur in a higher dimensional space, with our universe being a membrane that periodically collides with another membrane. Each collision produces a Big Bang. This model can accommodate dark energy and does not require the universe to contract. Another idea comes from loop quantum cosmology, a theory that tries to combine general relativity with quantum mechanics. In this theory, the singularity at the Big Bang, the point of infinite density that standard cosmology predicts, is avoided. Instead of emerging from a singularity, our universe might have bounced from a previous contracting phase. The equations allow you to extend time backward before the Big Bang, into an era that was like a mirror image of our expanding universe. Yet another idea comes from string theory and the ekpyrotic scenario. In this picture, our universe is a three-dimensional membrane floating in a higher dimensional space. Occasionally, two membranes collide, and the collision energy produces a Big Bang in each. Our universe might have been produced by such a collision, and there might be other membranes, other universes, floating in the higher dimensional space. These are all speculative ideas. We do not have observational evidence for any of them, but they show that physics has resources for thinking about what might exist beyond the Big Bang, beyond the beginning of time itself. There is one more thing I want to mention. Earlier I said we cannot see beyond the surface of last scattering using light. But light is not the only messenger from the early universe. There are others. Gravitational waves can travel through the primordial plasma without being scattered. If gravitational waves were produced before recombination, during inflation for instance, they would travel freely to us, carrying information about that earlier era. This is why detecting primordial gravitational waves through their effect on CMB polarization is so important. They would be a window into the pre-recombination universe. Neutrinos also travel freely from the early universe. The cosmic neutrino background was produced when the universe was only about 1 second old, long before recombination. If we could detect these primordial neutrinos, They would carry information about a much earlier time than the CMB. Unfortunately, detecting the cosmic neutrino background is beyond our current technology. The neutrinos have such low energy that they barely interact with matter at all. But it is a goal for future experiments. Someday, we might be able to see the universe at 1 second old, billions of times closer to the Big Bang than the CMB allows. So, what exists beyond the cosmic microwave background? The answer depends on what you mean by beyond. Beyond in space? Almost certainly, the universe extends far beyond what we can observe. Inflation suggests it might be vastly larger, possibly infinite. There might be regions with conditions like ours, or regions with different properties entirely. We will probably never know for sure because we can never see them, never send signals to them, never receive signals from them. They are beyond our horizon, forever. This is a humbling thought. We have worked so hard to understand the universe. We have built magnificent telescopes. We have developed powerful theories. We have pushed our understanding to the edge of the observable universe. And yet, beyond that edge, there might be infinitely more that we can never access. The observable universe, vast as it is, might be an infinitesimally small fraction of the whole, but it is also inspiring. It means the universe is larger than we can imagine. It means there is always more to discover, even if some of it is forever beyond our reach. It means the cosmos is not small and provincial, limited to what we can see. It is vast beyond measure, perhaps infinite, stretching forever in every direction. Beyond in time? Before recombination, there was hot, dense plasma where the physics of the very early universe played out. We cannot see it directly with light, but we can infer its properties from the CMB and potentially observe it with gravitational waves or neutrinos. This is the next frontier. The CMB has told us so much about the universe at 380,000 years old. But the universe was doing interesting things long before that. Inflation, nucleosynthesis, the formation of protons and neutrons, all of this happened in the first few minutes. We want to see it directly. We want to peer through the fog of the early universe and see what happened at the very beginning. Gravitational waves might be the key. They can travel through the primordial plasma without being scattered. If we can detect the gravitational waves from inflation, we will be seeing the universe at less than a trillionth of a second old. We will be piercing the barrier of the CMB and looking into the hidden era beyond. Before the Big Bang? This is the deepest question, and we do not have a definitive answer. Time itself might have begun with the Big Bang, making the question meaningless. Or there might have been something before, a previous universe or a higher dimensional structure that gave birth to ours. The cosmic microwave background is a wall, but it is also a window. It shows us the universe at a specific moment in its history, the moment it became visible. Everything before that moment is hidden from light, but not necessarily from all observation. And everything beyond our horizon exists, even if we can never see it. This is perhaps the most profound realization of all. The universe does not care whether we can see it. It exists whether we observe it or not. The regions beyond our horizon are just as real as the regions we can see. They have galaxies and stars and perhaps life. They have their own histories, their own stories, their own observers looking out at their own cosmic horizons. We are not the center of the universe. We are not special. We are one tiny part of something vast, possibly infinite. The CMB reminds us of this every time we study it. It shows us the edge of what we can see and it hints that there is vastly more beyond. But in another sense, we are special. Consciousness examining its own origin. Matter contemplating the conditions that made matter possible. There is something recursive about cosmology. Something that closes a loop 13 billion years in the making. When you look up at the night sky, you're surrounded by ancient light. Every direction you look, at the very edge of what can be seen, there is this wall of radiation. It has been traveling toward you for almost 14 billion years. It carries the fingerprints of creation, the seeds from which everything grew. And beyond it, beyond the wall, beyond the horizon, the universe continues. Perhaps forever. Perhaps infinitely. Perhaps in ways we cannot yet imagine. We are small creatures on a small planet orbiting an ordinary star in an ordinary galaxy. But we've figured out this much. We have traced the history of the cosmos back to its earliest moments. We have found the echo of the Big Bang still ringing through the universe. We have decoded its message and learned that we live in a universe that is far stranger and far larger than anyone could have imagined. The cosmic microwave background is the oldest light there is. It marks the boundary of what we can see. Beyond it lies mystery. But mystery is not ignorance. It is invitation. It is the next question to answer, the next horizon to cross, the next wonder to discover. The universe has given us this gift, this wall of ancient light that speaks to us across billions of years. It tells us where we came from and hints at what might exist beyond. We are just beginning to listen. The story of the cosmic microwave background is, in many ways, the story of human curiosity itself. For most of our history, we did not know this light existed. We walked beneath it, slept beneath it, lived our entire lives bathed in radiation from the beginning of time, and we had no idea. The CMB does not care whether we notice it or not. It has been there all along, patient, eternal, waiting to be discovered. What changed was us. We developed tools, we built telescopes and radio antennas and satellites. We created mathematics that could describe the behavior of matter and energy at the dawn of time. We asked questions and refused to accept easy answers. We looked at the universe and demanded that it reveal its secrets, and the universe answered. Not with a voice, not with intent, but through the language of physics. The CMB is a message written in the fundamental laws of nature. To read it, you have to learn the language. You have to understand how light behaves, how matter behaves, how space and time behave. You have to build instruments sensitive enough to detect variations of one part in 100,000. You have to develop computers powerful enough to analyze the data. You have to create theories and test them against observations. This is what humanity has done. And the reward is knowledge. We now know things about the universe that no previous generation could have imagined. We know its age, its shape, its composition. We know it had a beginning, and we understand the first moments of that beginning. We know there are mysteries beyond what we can see, and we have theories about what those mysteries might contain. This is the power of science. It does not give us certainty. It does not give us final answers, but it gives us a method for pushing back the frontiers of ignorance. It gives us tools for asking questions and finding evidence. It gives us the cosmic microwave background, a window into the past that no myth or legend could have invented. The CMB reminds us that we are part of something vast. The same physics that governed the early universe governs us. The same fluctuations that appear in the ancient light became the galaxies that contain the stars that support the planets that harbor life. We are not separate from the cosmos. We are the cosmos, evolved. We are ancient light that became complex enough to ask where it came from. And perhaps that is the deepest message of the CMB. We come from everything. We are connected to everything. The wall of ancient light is not a barrier that separates us from the universe. It is a reminder that we are made of the universe, shaped by its laws, products of its history. When we study the CMB, we are studying ourselves. Thank you for joining me on this journey to the edge of everything. We have travelled further tonight than most people ever imagine. We have seen the oldest light in the universe, decoded its secrets, and peered at the limits of what can be known. If you found this exploration meaningful, please consider liking this video and subscribing to the channel. Your support helps me continue making these deep dives into the cosmos. Every subscription, every comment helps spread these ideas further, helps more people understand their place in the universe. And the next time you look up at the night sky, remember what is out there. Beyond the stars, beyond the galaxies, beyond everything you can see, there is a wall of ancient light. The first light that ever traveled freely through the universe. The edge of the visible cosmos. The stars you see are beautiful, but they are recent arrivals. They formed billions of years after the CMB was released. The galaxies you see through telescopes are impressive, but they are structures that grew from the seeds planted in the CMB. Everything visible in the universe is younger than the ancient light that surrounds us. The cosmic microwave background is out there, surrounding you from every direction. It has been traveling toward you for almost 14 billion years. It carries messages from the beginning of time, and beyond it lies a universe vaster than we can imagine, stretching perhaps forever into mysteries we are only beginning to explore. We are made of matter that condensed from fluctuations in that ancient light. We are literally the children of the CMB, the grown-up versions of those tiny ripples that appeared at the moment the universe became visible. When you look at the cosmic microwave background, you're looking at your own origin. You're looking at the seeds from which you grew. Consider the journey. 13.8 billion years ago, a tiny fluctuation in the primordial plasma made one region slightly denser than its neighbors. This was not a dramatic event. It was a whisper of difference. 1 part in 100,000, almost nothing. But almost nothing is not nothing. That tiny whisper would echo through cosmic history. Over hundreds of millions of years, that fluctuation grew. It attracted more matter. It collapsed under its own gravity. It became a galaxy. Within that galaxy, clouds of gas collapsed to form stars. Those stars burned through their fuel, forging heavier elements in their cores. When they died, they scattered those elements into space. New stars formed from the enriched gas, planets coalescing in the disks around them. On one of those planets, chemistry became biology. Simple molecules combined into complex ones. Proteins formed, cells appeared. Life began its long journey toward complexity. Over billions of years, life evolved, becoming more complex, more diverse. Eventually, on this one planet orbiting this one star in this one galaxy, creatures evolved that could think, that could wonder, that could look up at the sky and ask where they came from. And the answer is, from a tiny hotspot in the cosmic microwave background, from a fluctuation in the primordial plasma, from a seed planted at the moment the universe became visible, from quantum uncertainty stretched across the cosmos, from the very fabric of space-time itself. This is your ancestry. This is your origin story. Not myth, not legend, Not speculation. Science. Measured and verified and confirmed by observation. Written in ancient light that has traveled across the universe to tell us where we came from. You are the universe, knowing itself. You are ancient light that became conscious. When astronomers study the CMB, they are not studying something separate from themselves. They are studying their own origin. Every atom in their bodies was once part of that primordial plasma. The fluctuations they measure are the seeds from which they grew. The ancient light is their ancestor. This gives the CMB a personal significance that goes beyond scientific curiosity. It is not just data, it is history, it is identity, it is the answer to the most fundamental question any conscious being can ask. Where did I come from? And the answer's magnificent. You came from the beginning of time. You came from the moment the universe became visible. You came from ancient light that has been traveling for almost 14 billion years. You are the endpoint of the longest journey imaginable, the destination of photons that have crossed the entire observable universe to reach you. Sleep well under the stars. And remember, you are surrounded by the oldest light in existence. It has been waiting almost 14 billion years to reach you. Good night.